Hello again, everyone. I'm Endi, one of the senior engineers here at Akamai, and this session is going to be a case study on how we built Egnatia, our lake house here at Akamai. Again, Endi, I've been here at Akamai for 5 years now. I started as an intern, did 2 of my co-ops over here, and yeah, I've been a long time. I want to talk a bit about Akamai. So the company was founded 25 years ago. We handle 30% of the world's internet. These are all of our regions. We're present in the world. We're mostly globally distributed at this point. We have around 350,000 servers. We're in more than 4,000 points of locations, 1,000 data centers, and more than 130 countries. So we work at global scale. But why are we here? Now, when I started working at my team 5 years ago, most of our data was coming from another different group, and it was processed in Perl. 5 years ago or 10 years ago, that was great, but today these scripts have started to show their age. They're extremely hard to work with. Perl is a beautiful language. It's very powerful, but like anyone knows here, with great power, there's a lot of responsibility. So there's more than one way of doing things in Perl, and that can quickly backfire. One of the issues that we had as well is that it is extremely hard, if not impossible, to backfill data. If we ever need to backfill, it means that we have to go back and rebuild the entire month. It's good when you have small data, but at our size, it's painful. The reason we have to build the entire month is because we get late data. We are on a global scale, so if a server in Australia is still yet to send us the data over, by the time we've already processed that in the US, we get some late data coming in, and that's going to mess up all our whole numbers. The way we're loading data affects your application. So essentially what we're doing is we use MariaDB as our warehouse, and we load data by using load data locally in file. What that does, it's going to send the whole file over to the master, and the master needs to replicate it over the workers. That's not good. Often our replication times, because of this, go to 1 hour, 2 hours, and at peak, sometimes they also go to 6 hours. Our team spend extensive time to keep things in shape. This is unfortunately because of the tools. It's a lot of legacy stuff, but we're slowly working to attack technical debt. We also have very little visibility in what's going on. If today we need to see if a specific file got processed or not, we have to log in the server. If we need to see if the whole data was processed for a specific day, we have to go and check a dashboard, make sure that the numbers that we got for that specific day don't deviate from the previous days. So with that, we had some requirements, so we need to make a change. So how do we do that? We need a simple architecture. My team only consists of 4 people, so we need to run extra lean. There has to be no third-party cloud. As some of you may know, we acquired Node recently, about a year or 2 ago, and now we have what's called the Akamai Connected Cloud. Observability must be a first-class citizen. What I mean by that is that at any point, if someone asks me, hey, and this is a question I get a lot, is the data processed for a specific day? I have to go in and check all the files, make sure the numbers add up and whatnot. I should know that by just looking at a dashboard. I should also know if a file, or what I call the journey of a specific file. So if I'm processing a file, I want to know if what stage it is in currently. It's in processing, it's being ingested, it's being reaggregated, and whatnot. We want seamless backfills. Again, if something breaks, I want to be able to just click a button and then replay the whole month easily, and then not break anything while doing that. This also means that I have to have idempotent pipelines. Idempotency is basically a feature that if I rerun something, it's going to rerun and not break anything else. Basically, the result is going to be always the same, no matter when I run it. We need to follow GitOps principles, something that is extremely important. That way we can track stuff in version history. We need elastic compute. What I mean by that is our infrastructure today is built on top of VMs. So once some pipelines are done, the VM is going to sit idle for hours and then not be used. And there's other VMs that run 24/7. But unfortunately, we cannot distribute the data across different VMs in this architecture because of the late arriving data. We need everything to stay in one place. So by having elastic compute, I can spin up as many clusters that I want, and then I can shut them down immediately afterwards. Most of our pipelines are batch heavy, so this works wonders for us. I want a low barrier of entry for software data engineers. Now, what do I mean by that? Many of us here, they onboard a specific team. You see the documentation is extremely out of date. Some of the tools don't work. Ideally here, I should be able to just run Docker Compose up and your dev environment just works. And that again is the other point. The dev setup should be able to replicate issues that happen in production as well. So essentially, what you have in development should be a one-to-one mapping of what's in production. We should be able to process hundreds of terabytes of data if needed. Again, this is also ties back to elastic compute. We use Spark today, and it's proved very, very handy for us. And the platform must be reliable. Things shouldn't break. And if they do, we should get alerted quickly when something breaks, not by a stakeholder saying that, hey, this dashboard is wrong. If in the data world, you never want a dashboard, a stakeholder knocking at your door like, hey, this dashboard doesn't look good. So what does all this look in practice? This is what we have, or what we're working towards today at Akamai on our data lakehouse. So I'll go over each component one by one, but basically our files, they're stored on Azure. Do you see my mouse? Yes. So our files are stored in Azure. We use DuckDB to ingest the data, dump that as Parquet on object storage, and then go through the whole medallion architecture. This is where the heart is, basically. It's all stored in Iceberg. And then we use Trino to serve all of this data. And I'll go over each component one by one. So what's our infrastructure as code strategy? So here it's an example on how we are going to deploy our clusters. So we're following a, so to speak, per component, per environment and region directory. So this is one of our ingest clusters. You specify your resources. This is how we bootstrap one of our Kubernetes clusters. Object storage, buckets, the access keys, any service accounts that are going to be needed to access Argo workflows or orchestration tool. We'll have the compute clusters, catalog, like Alex was speaking before. We'll of course need to run the multiple regions for redundancy and high availability. We'll also have a staging and dev environment. Now this is very good because this way you have a really small blast radius. So if I'm fixing something on LKE cluster on ingest in this region, the other resources are essentially not going to be affected if something goes wrong there. There's also clear separation of concerns throughout teams, and everything is stored in one branch. That's called the main trunk strategy. So main is going to be our source of truth. All changes have to flow through a feature or a bug fix or an infrastructure branch, and this ensures basically consistent and very stable deployments. We're going to have some quality gates. We're software engineers. We need to catch errors before they make it to production. So each pull request will have to go through linting, security scanning, formatting, validation, and whatnot. We are integrating Atlantis. For those of you who don't know, Atlantis is basically a tool that makes your Terraform pull requests very, very easy to test. If you're using Jenkins or GitHub Actions, you'll have to basically print your plans on the pull request or wait for the user input to approve that plan. Atlantis eliminates that. You can just run Atlantis plan or Atlantis apply, and it's going to apply your plans for you. If there's two pull requests trying to modify the same resource, it provides logging as well, so it's extremely important. So two pull requests will never try to basically modify the same the exact same resource at the same time. Jenkins is our tool of choice for CI/CD. We've been using it for quite a long time. We know how it works. There was no need to switch to a different tool here. So that's it in our infrastructure as code strategy. The next one will be our GitOps strategy. It's going to follow a similar structure: environment, region, cluster, and workload. We're using Argo CD. We are pretty invested in Argo. We can use Argo CD, Argo workflows. We're also looking at Argo events. The reason why we like Argo a lot is because it's very lean, Kubernetes native, and it just works out of the box. Basically, when you're on Airflow, you pretty much need a whole team to manage Airflow if you've worked with Airflow in the past, so it's pretty painful. Argo just works with very, very minimal oversight. So we have clear responsibilities here. Terraform will provision the clusters, and Argo will do the whole in-cluster deployment of the applications. This is all going to be on Git, so we can see, the version history of what goes on and what changes need to be deployed. DuckDB, you may have seen on the first slide here that we use DuckDB on our ingestion layer. I am a huge DuckDB fan, and we use it very, very heavily to clean and enrich our raw files. It is extremely fast, no JVM overhead, extremely feature-rich. You can pretty much do anything in DuckDB. I used to be very much against SQL. Thank you, Phil. But now everything I do in my database is from SQL. So I like DuckDB a lot because it produces very, very evenly sized files. And if you've ever written something in object storage, you'll know that small files will instantly kill the performance of any workload that you have. With DuckDB, I can say that I want files to be a maximum of 500 megabytes. I can modify the row groups for Parquet, and that allows me to have really good performance. And this pairs really well with Iceberg's add files procedure. What that means on the Iceberg side is that I can basically tell Iceberg that, hey, here's a set of files. I just want you to add these to your structure. And what Iceberg will do is it's going to go and only read the schema and the statistics of that file. It's not going to go and ingest the whole file. It only knows, it only does that to grab some statistics like min-max for columns and stuff like that. That's extremely helpful, and it's also very, very fast. So we cut our ingest times a lot by doing this strategy. And again, we have Iceberg. Alex talked a lot. I'm not going to spend too much on this slide, but we love Iceberg. It helps us do schema evolution. So if a stakeholder wants to change a specific column or add or remove more columns, we can easily do that. Time travel and rollback. I don't know if you've ever dropped a table in production. It's not a fun thing to do, but with Iceberg, you can easily bring it back. It's as simple as saying, create this table as a specific version. Data compaction comes out of the box. Transaction, extremely useful at scale and when ingesting data from multiple sources. Efficient reads, you basically skip unnecessary files when using Iceberg because of its statistics that it calculates for the files. And it knows automatically when you say, pick a specific file from this timestamp, it doesn't go and read the whole table. It just goes and then grabs the files from that partition. It allows for partition evolution and hidden partitioning. What hidden partitioning means is that you as a user don't have to know, where or how the partition looks like. You just specify that, for example, you want to partition your table by hour, by date, or by a bucket, and Iceberg will automatically handle that for you. It allows the write audit publish pattern. As a data engineer, I love this. It means that I can validate my data before even before publishing in production. Extremely useful for catching errors early. Again, we don't want errors to go in production. We want to catch them before they make it there. Upsert through merge. This is extremely useful for us. Again, our data is often late, which means that we have to do upserts constantly, and that's a very, very expensive operation. But it's at scale with Iceberg. It's worked really well for us so far. Trino. Trino is our serving layer. I like Trino a lot. Again, it's one of those tools where out of the box, it provides a lot of functionality. For us, it's a unified query layer. We can join it with multiple sources. Here at Akamai, we have a lot of silos, so this is a very good way to break through those silos. It allows for fine-grained access control, either through the Open Agent Policy, OPA, which is the Open Policy Agent Ranger, or you can do like something as basic as a file-based approach. You can get multi-cluster scalability via the gateway. Here's a very, very simple diagram on how we're thinking to deploy Trino for our company. Basically, we have the client applications who then connect to the gateway, and the gateway is nothing but a load balancer between all the Trino clusters. In the past, people had to be very creative when it came to load balancing multiple Trino clusters. The gateway was initially founded at Lyft, I think, who then open sourced it, and then the Trino community just took off, and then this became one of the Trino products as well. So with Trino, we are deciding on to have a, so to speak, types of clusters, so either ETL clusters or ad hoc clusters or machine learning workloads or aggregation clusters. It depends on the type of workload that we're running. And the beauty here is that they are all connecting to the same data, either through Kafka or object storage, which runs in Iceberg, or your Postgres or MariaDB or whatever database you have. So there's a clear separation of responsibilities here. The data stays in object storage, and you just have compute that just runs queries on top of it. It works really well. Every component does, it's specialized for only one thing. Orchestration. So this is what orchestrating a workflow looks like for us. We're using Argo workflows, but with that, we're using the Python SDK through Hera. Hera is basically a wrapper around the Argo workflow API. And for those of you who have looked at Airflow before, it's very, very similar to that. Here, we're specifying if we want to basically deploy a Spark job. So we read the Spark YAML. We specify that as a resource. We state the conditions when which is complete and where it's failed. We have some parameters. And then from there, we can easily schedule that workflow. Very, very Pythonic. I like it a lot. My team likes it a lot because we never have to type YAML. So we can always stay in the Python world. And also integrates really well with other types of workflows in addition to Spark. You can use it for machine learning. You can use it for AI. You can use it for ingestion, anything. It's really good. Again, it runs on top of Argo workflows, and we love Argo. It works good out of the box with minimal supervision as well. Observability. So I talked that this was going to be a first-class citizen for us. So what does this look like in Kubernetes? It means that it's as simple as adding an annotation to your job. So logging scrape or Spark monitor true. You're basically telling Grafana agent, our agent of choice here, to go and scrape the logs and the metrics from those pods. And just we basically offload those into a managed Victoria's Secret and Loki instance. I have tried Prometheus in the past, but again, it's one less thing I have to worry about. So we're using the internally managed Victoria's Secret, Victoria metrics here instance to offload all these metrics. Alert Manager handles all the alerting. We're using the DataFlint plugin for additional Spark performance monitoring. Then basically when we look at our Spark history logs and jobs, we can see, in addition to how a specific job performed, also the additional metrics that the DataFlint plugin exposes. It's really good. Now, the Volcano scheduler. If any of you here has tried to schedule a Spark job in Kubernetes before, and you tell it to use all of the resources, but then you have this very, very small job that only consumes 2% of your cluster resources, you're in a split brain situation. Basically, what's going to happen is that your Spark job is going to be stuck waiting for more resources to be available. And this is what's called gang scheduling. Now, with Volcano, which is a batch scheduler, we can have queues. And queues are really good because with queues, I don't need to be creative in my cluster sizes, right? I can basically say that, okay, I have a queue that has 200 CPU cores and 3 terabytes of RAM, and then we can use the queue accordingly. You can use all the resources, and you can submit as many jobs as you want, and it's just going to go to the first in, first out approach. You can do what's called hierarchical queues. So out of this main queue here, we can have leaves. So we can specify a sub-queue that consumes maybe 10 CPU cores and maybe 20 gigs of RAM, and we can hand that off to a team. That's really useful in a multi-tenant approach, because you can give each team a specific subset of that queue. You get job prioritization, gang scheduling, resource overcommitment. So this plays really well when we do auto-scaling, because we can tell the scheduler Volcano to have an overcommit factor. So if, for example, I have a job that requests 6 terabytes of RAM, but my cluster only has 20 gigs of RAM at this point, I can come up with some sort of math that's sensible enough to be like, okay, if the user is requesting, let's say, 200% more resources than we can have currently deployed, trigger scale up. And what Kubernetes will do there is it's basically going to create more, it's going to add more nodes to our cluster. So it's extremely good in cases where we don't know ahead of time how many workloads we expect. It's also good on batch workflows. So for example, all our scripts are nightly. They crunch some numbers to the night, and next morning, boom, you have some numbers. And your cluster don't have to sit idle. You destroy all your resources, and you only need what you need to, only use what you need to use. And there's also all sorts of plugins that come in with Volcano. It's an extremely good tool. I like it a lot. So this was all of the components that we had so far. With that, some future work. We used the Hive Metastore. When we started using Iceberg 3 years ago, there was no Polaris. So we're looking at Polaris now. The issue with the Hive Metastore is that you have to manage permissions to S3 keys. And tracking which user is using which user uses the specific key is really painful. Polaris takes care of that for you. You're essentially saying, grant the specific user access to this table. Credential vending is also a very, very, very cool feature that I learned on the Iceberg conference last month. Basically, you're telling your cloud provider to issue temporary credentials to access a specific table through the catalog. So you as a user never have to worry about keys or anything like that. And I as the engineer don't need to rotate keys all the time. I have the catalog do that for me by issuing temporary credentials. Spark accelerators. This is something that's picking a lot of heat recently. One of them is Data Fusion Comet. It's a Rust-based accelerator for Spark. These are extremely helpful because Spark represents data in memory as a row-based. So, and what these engines do, they basically convert that to column-based. Now that's extremely fast and important when doing these in scale and when doing crunching numbers in scale, because they claim to accelerate your workloads by 2 or 4 times. I haven't tested it yet. It's on my list, but I'll keep you guys posted. But it's something very promising. The industry is moving towards that. We have some workflows that require encryption. It's not GA at Iceberg. There's a pull request being reviewed currently. Once that's out, it's going to help us have encryption as well. InfoSec loves encryption. If you've ever talked to InfoSec, they'll tell you how everything has to be super secure so that there's no attacks and whatnot, and this helps. One of the things that we also want to work on is having support for event-based pipelines. So if we have a low latency workload, or if we want to react when a file is as soon as it comes, instead of having cron jobs that go check the state of what files we processed and versus what files we have, these are very important. So we're looking at this through Argo events, integrates really well in the Argo ecosystem, and it works out of the box with all the Argo tooling. With that, thank you so much, and I'll open the floor for Q&A. Okay, going once, going, oh, Alex, yep. So the question is whether we're looking to use Data Fusion in another way. Initially, when I first discovered DuckDB, there was also the the vanilla Data Fusion, right? So I was torn between whether do I want to use Data Fusion or do I want to use DuckDB, and I eventually ended up using DuckDB for the only reason that it was extremely simple to install. Data Fusion is amazing, but it excels as when you want to extend the query engine, right? So while DuckDB is like batteries included, with Data Fusion, you have to, let's say that I want to build a custom workload to read some proprietary formats that we have at Akamai for the data. I can do that with Data Fusion. I cannot do it with DuckDB. So for this use case specifically, DuckDB just crossed all our boxes. Yes. So table maintenances are automatic. So on our ingest layer here, this one. So on Azure, we basically currently move data to a cold tier after 45 days. In our object storage, the raw data is expired after 90 days. There's some tables that are really big, so we expire those after a month or 2 weeks. And then once a file gets ingested into Iceberg, the Iceberg tables have an automatic compaction, automatic snapshot, expiring, removing orphan files, and it goes through the whole Iceberg's journey of maintenance, basically. So that's all automatic. So for each table, we then, what we do now, it's once per week. So that's how often we do these maintenances, for the only reason being that our tables are copy on write, which means that when we write the table, part of the writing is also compacting the files. So that's really helpful for us. And also it's because we have batch workloads. If we had something more real-time, we'd switch to a merge and read strategy, which means you just write the files and then you have to do compaction separately. That's mostly used for lower latency workloads. So we only use Iceberg. I haven't looked at, I looked in Delta 2 or 3 years ago, but it was mostly Databricks contributing to it. And at the time, I didn't felt comfortable using Delta Lake, the open source version, just because you never know what might happen. They just switch the license and all of a sudden you're stuck and then you don't know what to do. There's also Hoodie that came from Uber. It's really good, but our workloads weren't real time. And Hoodie is mostly used for real-time purposes, I've seen in the industry. We do have some, I am working with another team that has a real-time requirement coming up. So that's going to be my evaluation of Hoodie, basically, and how Iceberg can react to streaming and low latency workloads. There's some teams that can make Iceberg work in low latency workloads. I haven't tested it yet. It should be doable if you cache the data. The frequently accessed one, I haven't tested it yet. So yeah, for us, it's only Iceberg for now. I guess. So right now, we do that through Argo workflows. So when a file lands here on Azure, we just do a cross-check on what we processed versus what we got. We're not doing event-based processing yet. So because I don't want to spend a lot of compute, these files are often 50 to 60 gigs big, but I only use 16 gigs of RAM and 4 cores to process them. And I was showing Alex earlier, it takes about 5 minutes of we have around 20 to 30 joins, types of lookups, and then we crunch the data and whatnot, and DuckDB can do that under 5 minutes. So the strategy that I take here is that instead of spawning up let's say 6 jobs to process 6 files in parallel, I can do it one by one. Because the requirement isn't to have it data fast, right? Correct, yeah. Like think as a cron job but through Argo workflows, yeah. Cool. Any other questions? Cool. All righty, thank you so much. All right, so the next session is going to be from Sean.